All right, so recording is officially going. It's Tuesday, September 7th. Come back from a nice long 3-day Labor Day weekend, and we have a 4-day week, which is actually pretty perfect for, I think, for what I want to cover. So here's what I want to cover this week. Do some principles and problems with you guys. That's this page here. I picked my favorite problems from your guys' textbook. So we'll do those. Now, speaking of this, see that's going to be our main focus today. Talk about a couple other things, but I'm going to pick up some problems from either this page or you guys remember that one. What's the other page? It's there you go. You guys remember doing some projectile problems too that look like this? This page was also with boxes, but it had 6 different projectile scenarios. Right? So what I told you guys to do was between these 2 pages collectively, just pick 8 and write them up and determine, and then that is due this coming Friday. Follow along in class. We'll do like at least something in class. Right? We're going to do a bunch of them today. Right? As many as I can do. Okay. I think at the time I had in mind, well, it seemed like a good idea. Like, hey, I've got like all these problems, so like picking an 8 seems pretty straightforward. I think in retrospect, that's been kind of a confusing way to assign that. So in the future, I think what I'll probably do is like pick specific problems for you guys. Probably make it a little bit more straightforward. Okay. There's got you guys' lab about ready. There's your quiz. So I'm gonna give you guys a take-home quiz on Thursday. So do a couple more days of stuff. Give you guys a take-home quiz. I think I'll have that due on Monday. So yeah, if you want to do it Thursday night, bring in Friday, then if you're done with that, give me a few days to do it then. Anyway, I'll get that to you guys by the end of the week. Now, some of you guys have turned in flip books, and I said if you did turn in one, then I'll show it in class. So I've got a small stack here. Let's take a look at some of these. Ooh, uh-oh. Oh, look at that. That is so awesome looking. This one's really good. It's kind of hard to flip, though. But ooh, yeah, good projectile there. Oh, this pink one I like a lot. Yes, penguin. That's red ball. Oh, this guy. It's a blobfish under the sea. Oh, shark. Got a UFO. Going up the roof. What they do. Oh, okay, that's all of them. Right. That's all I've got here. So those are, yeah, you guys did a really good job with those. It's really awesome. Now, tomorrow we're gonna have a lab for you guys. So I do want to tell you guys a little bit about the setup so that when you walk into class tomorrow, you'll know what you're looking at. You're gonna have you guys figure out what is the launch speed of a launcher. Okay? Your setup might look a lot like the starter question here that some of you guys may have already solved by now since you guys have been looking at it. Okay? But the launcher looks like this. Show it here for the video too. Okay? And there's this little yellow ball. Put that right here. Okay? And you guys see the spring, so you can see from the side what it's going to look like. Now, if you listen real close, you guys heard it click into place. Right. Now it's spring loaded, ready to go. And all I have to do is pull this yellow cord and bam! So, I wonder what the firing speed of that is. But you know what I really wonder what the firing speed is? Uh-oh. Gotta get back. You guys hear that click? You guys hear 2 clicks? 2 clicks? It's 2 clicks. Oh, now it's really gonna go. And back. But wait. 1 click. 2 clicks. Get in there. 3 clicks. Right, so play safe tomorrow. That's going to be a fun project. I wonder what the firing speed of that is. Time will tell. There's a whole lab. Yeah, it's a great segue to this starter question. Suppose you had a setup that looked like this. There was a launcher at the top of this cliff. Now I gave you guys some numbers. I said a 7-meter tall cliff, and you go, let's say it's like 5.5 meters out. Could you guys figure out what the launch speed of that scenario is? Did anybody solve it? Does anybody know how fast it's going? No? All right, so I think you guys do this thought process, and then we'll work it out with the numbers. What I'm thinking is however fast it's going. Like once it's in free fall, like this whole dash curve shape of a parabola, right? Doesn't it go constant speed across, just constant horizontal speed? Right? And if it went this far horizontally, like 5.5 meters, and whatever the fall time was, couldn't I just divide those two? Say this distance divided by the fall time? That would be the launch speed, wouldn't it? Oh, so maybe this is real straightforward. But then it's like, well, what's the fall time though? And isn't that constrained by this fall height? Right, the 7 meters. Right? So maybe that's what you should do. Maybe that's our roadmap. Is first I'm going to look at this dropping height, say how many seconds does that take to happen, and then I'll look back over to the horizontal stuff and say, well, it went this far in that much time, and then divide those two. Okay. The way that we were doing this with, hold on a minute. I just have this here. With the page boxes was, I gave you guys some horizontal information, some vertical information. I said time is the one variable you're allowed to transfer. If you guys like that framework, then okay. We're doing that just a little bit more informally. Okay. So I'm going to start with this height, this 7-meter drop height. Okay. And wouldn't it be true that the height it falls is 1/2 GT squared? Right? Is that true? Okay. It's just like this poster that's hanging in front of me. You guys see it, this one right here, how far it falls, 1/2 GT squared. Okay. And we're solving for how much time, because remember, once we get that time, you just take this distance, divide by that, and it'll tell us what the launch speed is. Right? So this is the first part. Okay. Now I'm going to plug in some numbers. I know this thing fell 7 meters, so it traversed 7 meters vertically. And it did that, well, it was picking up speed at a rate of 10 meters per second squared. That's what G is. Can I go back and extract that time? Hey, just do some algebra and I could do that, right? So let's see, multiply both sides by 2, divide by 10. So 2 times 7 over 10. The meters would cancel, you have seconds squared. That's equal to time squared. Then shouldn't I just square root both sides? Square root. Bring in a square root. What is the square root of 2 by 7 over 10? Okay. That's telling me the falling time was 1.183 seconds. Oh, okay. Now, that's too many digits. That's way too precise, but I'm keeping them anyway just because that's a middle step. Right, so I'll save the rounding for the end. Right. But about a second. Can I believe that? Well, guys, on Earth, how far does anything fall in 1 second?
5 meters.
Yeah, 5 meters. You guys remember that? 1/2 GT squared, plug in 1 second, falls 5 meters. And this is a little bit more than that. So yeah, this looks reasonable. I can believe that. All right. Well, now let's switch over and look at horizontal because all this stuff was all vertical. Right? Okay. Now let's switch over to the horizontal analysis. I'll say you could either start with this, distance equals speed times time, just in the horizontal direction. Or if you want to rearrange it from the start, you say speed is distance over time. Okay? And this is all going to be horizontal. Okay? We've got, it went 5.5 meters across. And it did that all in 1.183 seconds. What's that? So then divide those two numbers out. What is 5.5 or 1.183? That is 4.65 meters per second. There you go. That would be the firing speed. Okay. What if you did this? What if you quadrupled the firing speed? Do you guys think it would go 4 times as far? If it was 4 times as fast, you think 4 times as far? Yeah, because it's 4 times fast here, it's going to go 4 times as far. Right? So that's a linear relationship between this speed and this horizontal displacement. But what about this? You guys ready for a trickier question? What if you were to quadruple the height? Would it also go 4 times as far? How many guys say, let's just make it yes or no. Let's see, show hands. Okay, so we'll repeat that question. Okay. So we do know that if you quadruple the firing speed, it would go 4 times as far because this relationship right here. Okay. But that's not what I'm asking. What I'm asking is, what if you kept the firing speed the same, and you just took this height and you quadrupled that, made it like 28 meters tall, just quadrupled that height? Okay. Would it still go 4 times as far? Okay. So let's do yes or no. How many guys say yes it would? 4 times the height would be 4 times as far. Who says no? It's just going to be something different. Oh, look at all those hands. Right? You guys are right. What if you guys can get this more exactly? If you quadruple the height, who can tell me exactly how many times further it goes? Well, remember the middle step was to solve for time? So maybe that's actually a good miss-up question. Right? Guys, if you quadruple this h, right, isn't that that height, whatever it is, going to become square rooted? What's a factor of 4 square rooted? What's the square root of 4? 2, which means it's been free falling for only twice the time. Interesting. So if you quadruple the height, it only falls for twice the time. Huh. And if it's been free falling for twice the time, you think it's going to go exactly twice as far? Yeah, because if you double that t and leave v the same, then x is also twice as far. Okay, so that's a little bit further than I originally take. I'm just going to take a guess. But, make sure I hit all this stuff. Okay, yeah, I think we're ready to go. So principles and problems. Yeah, principles and problems. All right, so this is from chapter 3, accelerated motion. And if I was writing your book, I would have written these chapters would have organized them a little bit different. But we got what we got. There's some linear stuff. There's some projectile stuff. So I'll kind of extend here. Okay. Let's start with these graphs, though. Ooh. I really like graph problems. Number 74. I see number 74. Okay. Now, these are all displacement versus time graphs, and they want you to make velocity versus time graphs. So, yeah, let's do all of them. For the second velocity versus time graph, think like a sideways t. Makes sense. It works out. Right. So this is displacement versus time for all of these, x versus t. Okay. And then I'm going to make up some curves that look very similar to those. Let's say you had like a parabola shape. Say had some shape that looked like this. Not exactly what's in your book, but pretty close. Right? And what if you had something that looked like this? Yeah, not exactly what's in your book, but pretty close to it. Okay. So I came up with my own curves that are pretty similar. Okay? And then could you make velocity versus time graphs for each one of these? Velocity versus time. How's it going? Okay. With a question like this, see if you can stay a step ahead of me. See if you can draw the velocity versus times before I do. Because if you can, then you know how to do this. Okay. Well, the first one looks pretty much like a parabola shape, doesn't it? Okay. You guys remember dropping the ball off a cliff? Isn't the answer like right here? Right, so if x versus t is like a parabola, then v versus t would be increasing at a constant rate. Right? So that's the answer to that one. Right? And if this is the vertex of the parabola, if you thought it was, then wouldn't it have to start from rest? Something like that? Right? Is that? To say these are 3 completely different scenarios, right? So 3 totally different scenarios, not related to each other. So scenario 1, scenario 2, scenario 3. Right? About scenario 2, right? Give you guys some position versus time to look like that. What would velocity versus time look like? Right? There's a reason I made it a sideways t, because there's going to be negative velocities and positive velocities. Hopefully you guys see what's going on, but if you don't, let's throw some seconds on the board and see how this works out in terms of like the seconds ticking by. So time's ticking by, here's time 0, tick, tick, tick. looks like maybe somebody's just walking in a straight line. Remember, these could all be linear motions, so it could just be like walking back and forth. Okay. Looks like they start out some position, and then they're walking in the negative direction, but at a constant rate. They say they're just walking back at a constant rate. Okay. Isn't that a constant negative velocity? And constant negative velocity, did you guys draw that? Is that what you guys just drew? Constant negative velocity? Okay. At this point, they hit a corner. Well, on the graph, it's called a corner. Looks like they immediately changed their walking motion. Now they're going forward in time. Right, this bunch of time. Right. And also really fast. Like if you compare these slopes, it looked like they were going backwards kind of slow and then moving forward really fast. Okay. So those two ideas in mind, okay. I'm definitely going to have a positive velocity. Okay. And it's said it has a magnitude that's greater than the negative velocity. Okay. Well, I should have made that more pronounced, but this is only like negative 3 meters per second. This might be positive 5 meters per second, something like that. Okay. Is that? And then, what about this last one? Okay. Well, I see something special going on at this time. Okay. What happened to this time? How did this person change their motion? Started walking how? It's faster, right? Looks like they were gaining positive distance with time originally, but just at a really slow rate. Okay. And then at this time, they started going really fast in the positive direction. Okay. Now, keep in mind that motion of this person is just in a straight line. All they're ever doing is just walking forward, just at different rates. They started going kind of slow. Okay. And then at this point, just really fast all of a sudden. There you go. Okay. Now, in math, these are called corners on a graph, and then the rate change of that is called a jump. Right? You guys see like a jump? Okay. Now, if you had actual physical data, it might just be a really fast turn. So it might be something like this. This might just be extremely curvy, and this might be extremely curvy, like type curve, and this might be like a slice of something like that. Yeah, you guys got this? All right, let's check out. I like this next question. It says, suppose you go to, it says Jupiter. Let's just say in general, some other planet that has a gravity field that's much stronger than it would be on Earth. Okay. So put Earth here. This is, again, I'm going to make up my own problem, but I'm going to make it very similar. I'm going to go to planet X. Okay. And on Earth, where there's Earth gravity, I'll just call it G, which is 10 meters per second squared about. Okay. Let's say on this planet X, the gravity of planet X is, let's say it's 5 times Earth gravity. 5 times Earth gravity, which would be about 50 meters per second squared. Okay. So not exactly what's in your book, but same idea, right? We're increasing the gravity. Okay. And what it says is, suppose you take a ball and you throw it vertically upward with the same speed on both planets, planet Earth and planet X. Right? Same speed. Right? How does the maximum height on the ball on planet X compare to the one on Earth? How does the maximum height compare? Well, if you want to know maximum height based on throwing speed, notice they didn't mention anything about a stopwatch being in the scenario, right? I'm thinking this. If you look at those 3 equations up there, you guys see those 3 equations hanging from the ceiling? There. These 3 guys? Right. Which one would most immediately answer the question, if you throw it up at a certain speed, how high does the ball go? First, second, or third? Right. Okay, so I've got a proposal for the first one. Now, here's the thing with the first one, is you want to know how high it goes, but they didn't mention how much time, right? Okay, so it's like sort of 2 unknowns. Okay? Maybe you know something about the gravity and something about initial speed. Okay? What I'm looking at is, see this very last one. Right? This last one, you can get it without knowing the time, right, of motion, because otherwise you need that middle step. So maybe you could do it that way, system of equations, be really long way solid. This third way, here, if I make a little tax-PV checklist. See, if you throw a ball straight up and it comes straight down, right, versus on planet X, like she's probably a lot shorter, right? I wonder how those heights compare here to here. Okay. Oh, well, I know on Earth it's just Earth gravity. I can call it G. Okay. And on this other planet, it would be like 5 times the gravity, 5 times Earth gravity. Okay. Here's what I want to compare. What's the height on Earth? What's the height on planet X? Okay. Okay. And at the same throwing speed, okay. Notice there's no numbers with any this question, okay, other than the multiple of 5 times the gravity. Okay. And here's where this is all going to come together, because I'm trying to solve for that, right? So that's an unknown. Okay. But final velocity, because if you throw a ball straight up, it comes down, and you want to know something about maximum height. What is the velocity at the maximum height point?
0.
0. So actually, you do know this number. It's 0 meters per second. Okay. That means you have 3 things, and you can solve for that right away. Okay. So let's try that. Okay. So I know that. Let's try it. So final velocity squared equals initial velocity squared. Okay. Now here's where, say 2ax. Okay. If I want to keep it in general, I might say that. I can modify this equation. I'm going to modify it for the scenario. At maximum height, Vf is going to go to 0 meters per second. Okay. Here's their throwing speed, call it V naught. Actually, sorry, I didn't mean to box that. It's squared. Okay. Now, here's where I'm going to modify this a bit. If I throw it upwards and I call it up positive, then isn't gravity pulling down? So I should say minus 2g h max. Okay. Here's what we're actually honing in on, that h max. Right? Sure. Okay. All right, so 2 algebra steps. I'm going to subtract the v naught squared over. V naught squared equals, looks like that. Don't the negatives cancel? So divide both sides by 2g. So over 2g. Okay. And now what I've got is h max, and this would be on Earth, is equal to, well, actually, you know what? It's a general expression, so I guess it's true for any values that you plug in. Okay. We have an expression for how high you can throw something based on how fast you throw it, and also what planet you're on. Right? So now I can plug in any throwing speed I want. I can plug in any planet I want, and I can figure out what the maximum height's going to be. You see it? It's all from, it's just a rearranged form of that third equation. Okay. But now we need to interpret it for this particular problem. So you go to this new planet, planet X, where gravity is 5 times as much. Okay, so we're looking at a relationship between these 2 variables. Guys, if you pump up gravity by a factor of 5, what happens to the maximum height? You guys see it becomes 1/5? Because if I multiply a factor of 5 in the denominator, see height is going to come up to 1/5 of what it would be? That's the answer. It goes 1/5 as high. Yeah. That's the answer to that one. Now, there's a follow-up question. It says, if the ball were thrown with, let's say a velocity of, well, they went 3 times as much because they're doing Jupiter, but on mine I'll do like 5 times as much. What if you threw it upwards with 5 times the initial speed, but also you change places at the same time? So it's like we've got 2 variables that we're juggling at the same time. So h max, clean up what I said from that last one. Finish this down here. So h max on planet X would be v naught squared on 2 times 5g, right? Okay, I'm just cleaning this up from before, which is equal to h max on planet X is, see, I could take out that 1/5. It would just be v naught squared divided by 2g. Okay. And this was the original h max on Earth. So I could say h max on planet X is 1/5 of h max on Earth. Okay, so we did that already, right? We're done with that one. Now I want to know, what if you throw this ball with 5 times the speed straight up, 5 times the speed. Okay? I'm still going to play off this expression, but it's going to work out differently. Right? What it's going to go is, there should be a side-by-side comparison like this. H max for Earth. Let's just call it V naught squared on 2G. I just copy pasted that, right? Versus what is H max on planet X? Now we're changing 2 things at the same time, right? On one hand, the gravity just went up by a factor of 5, so it'd be 5 times Earth gravity. Okay. But also, you're throwing it 5 times as fast. Okay. You guys see it's going to be set up? Okay. So this is throw times is 5 times as fast, and this is 5 times the gravity. Okay. Now, I should have asked you guys before I write that down, but maybe you see it now, maybe you don't. I'll go ahead and ask you this question now. If you're on a planet with 5 times the gravity, and you throw something up, well, it doesn't want to go as high, but if you throw it 5 times as fast, maybe it should kind of compensate for the extra gravity pull. Right? But is it going to be a wash? So if you throw it up 5 times as fast and 5 times the gravity field, right, is it going to go to the same height as it did on Earth with just the original speed, original gravity? Or is it going to be something different? Right, so let me see, show hands. How many guys think that 5 times the throwing speed, 5 times the gravity exactly washes out? And who says something different is going to happen? Something different. Ooh, all right, I see a bunch of hands there, and you guys are right. And all we have to do is finish this out and compare it to the original value. Okay? So H max on planet X. Okay? And the key is that the 5 times throwing factor gets squared. And that's going to make all the difference. Okay, see, it's going to be 5 squared is 25. And then down here, well, there was just a factor of 5, right? I'm going to factor those out. And I'm left with a V squared up here. And I've got a 2 times G down here. Right, you guys got it? And oh, look at that. This is this. You guys see that that's H max on Earth? Okay. And if that's true, then in 25 over 5, that's equal to 5. Then I can say H max on planet X is equal to 5 times H max on Earth. Okay? That was for the scenario 5 times Earth gravity, but also 5 times the throwing speed. Right? So if you're on Earth, you throw it up at some speed, it's going to go to some height. You're on this new planet with 5 times gravity, you throw it up 5 times fast, it actually ends up going 5 times as high. Right? So throwing up faster actually makes more of a difference than the increase in gravity, right? Because it's being squared. Okay. Guys get it? Right. Yeah, so that's the problem in terms of variables. Oh, it's pretty fun. Ooh, I like this next one. It says a police car. It says a police car is, a speeding car. A speeding car is traveling at a constant speed. They give you a number. When it passes by a stopped police car, the police car then accelerates at so many meters per second squared. How fast is the police car going to be going when it catches up to the speeding car? Okay. So I'll draw this out. I'll make up my own numbers, and then you guys can follow along and see you guys kind of get your own too. So scenario: we got a stretch of road, a little dash line of the road. Okay. We got this speeding car, and I'm going to give it a speed. Just call it V sub. Call it blue. I'm going to call it V sub B, B for blue. Okay. Let's call it 40 meters per second. Okay. That's good speed. Okay. Okay. And then here we got this cop car. And the cop car starts from rest. Right? Oh, I'm so sorry. Right there. Okay. So we're back there. Right. So blue car zipping along at that speed. Right. There's a cop car just sitting there parked. Right. And he's got a radar gun on. Right. And as soon as this guy reaches like this frame right here, the snapshot, this police officer steps on the gas and starts speeding up. Right. Starts speeding up. Right. And eventually catches the blue car on down the road. It's like at sometime later. Okay. Now, let's say the guy's speeding. He's just going at his speed the whole way. It's just a constant value. He just keeps going. Right? But the cop car had to speed up to catch him. Okay? And that's the question: is what is? Well, I'll call it. Let's do C for a cop car, right? So V naught C was just 0 meters per second. Okay. And what is V final for the this car? Okay. That's the question. Okay. Guys get that? All right, so that's the setup. That's the premise. Let's try to color in these cars. That's what I do. The car versus that car. Right. Now, before I get chugging on all the math side of this, let's think intuitively. Can you sort of maybe figure out some stuff even before we get to that point? Right? Like, if this blue car flew by and had a good head start, and then this red cop car has to catch up to him, do you think that by the time that this red cop car does catch up to him, he's going the same speed or faster? What do you guys think? Faster. It's got to be going faster. As long as he's accelerating uniformly, and that's all he does, and that's part of the premise of this problem. Right? He's not like tapping the brakes when he's catching up. No, he's uniformly speeding up. Right? So each of these cars has an equation to govern their motion. And the key that's going to be able to let us solve this is that they are at the same place at the same time. You guys see that? You guys see same place, same time? Okay. That makes me think, hey, we could set up a system of equations, position versus time for each car, and then set those equal to each other, same place, same time, and then just solve for stuff, right? That's going to be our approach. Well, let's see where this goes. Okay. Now, it might not answer this question right away, but it might solve for the time. Maybe it's like so many seconds now, and then we could figure it out from there. That's it. So for the blue car, just very simply, its position is 40 meters per second times however much time has passed. That's it. Got a couple of variables, independent, dependent. Well, that's the whole thing. Now, the cop car is a bit more involved because the cop car is speeding up from rest. So the position of the cop car, this could be blue car, this is cop car, okay, is, well, it started from rest, so that's V naught T, but V naught was just 0, so I won't even write that. Okay. Plus 1/2 times the acceleration times time squared. And I forgot to give you an acceleration value, but let's do that right now. So let's say this cop car is speeding up at, let's do 6 meters per second squared. Okay. So we got 6 meters per second squared times time squared, right? Because isn't that 1/2 AT squared? Okay. And this right here is your system of equations. Okay. So they each have a position equation as a function of time, right? And then, okay. Now remember back to this right here. If they're at the same place, same time, does that mean I can just take these two and set them equal to each other? Because that would be at the same place, wouldn't it? And I could just solve for the time that happens. You guys see that? Okay. You guys able to stay a step ahead of me for each of these steps? Okay, so I'll do that. I'll set those equal to each other. So I've got my 1/2 AT squared equal to speed times time. The blue car, right? Yes, sir. Okay. Do you guys see? Okay, you guys get that with that so far? Very right. Any questions so far? All right. So I've got their position equations set equal to each other. Do you guys see that at time 0, that's actually going to be one of the solutions? Time 0, because then 0 meters would equal 0 meters. That lines up with this frame right here. Okay. But we're really more interested in this frame. Yeah, the fast way I could do this, I could just divide both sides by t. Then I've got 3t is equal to 40. And some units. meters per second cancel. I left both those second. Okay. So it looks like time is going to happen at whatever 40 divided by 3 is. What is 40 divided by 3? 13.33 seconds. 13.33 seconds. Okay. Is that all right? All right. Now, that's not the answer to the question, but that's a good middle step, right? Because now we know that this whole process took a little over 13 seconds from here to here, right? And we could go different ways with this. We could figure out how much road did that take by plugging it back to the original questions, but that wasn't the question. So the question was how fast the cop car going. Right? So now let's create a new equation for the cop car, and since we know the time, we'll just plug that time in. Right? You guys see that? Right. Let's try that. Yeah. So let's go. The speed of the cop car equals the original speed plus acceleration times time. Right? Or you could have gone v squared equals v naught squared plus 2ax, but that would have been an extra step because you have to go back and solve for x first. So this is the fastest way to do it. The original speed of the cop car was of course 0 meters per second. Okay. The cop car was speeding up at 6 meters per second squared. Did that for 13.33 seconds. Okay. Now, again, that's way too much precision for the time, but it's okay because it's the middle step. I'll save the rounding for the end. And the final speed of the cop car is 80 meters per second. That's the answer. Okay. Now, take a look at that speed, 80 meters per second, compared to the blue car was going 40 meters per second. You guys see that's a 2-to-1 ratio? Do you guys think, you guys ready for a crazy concept? Do you guys think that I could have made the cop car accelerate at any value? I picked 6 meters per second squared, but I could have made that 5 or 15 or any number. And the answer to this question is always going to be twice the speed of the blue car. Sure would be. Let me show you guys an alternate way you could have solved this. You could solve this really quick with a graph. Would it look like this? Speed, time, blue car. I'll make it really generic. I'll just call it the blue car. Okay. Here's the cop car. Starts to rest at time 0. Catches up to the blue car. And do you guys remember what property of a velocity versus time graph tells you position, or displacement, I should say? How far? You guys remember it's the area under the curve? Because it's got meters per second times seconds. That gives me meters. Okay? And if you look at a couple things here. Here's how far the blue car went. It's the area of this rectangle. Speed times time. The speed times this time. That's it. Okay? That's how far that represents how far the blue car went. Here's how far the cop car went. It's this whole triangle right here. Okay. Do you guys see that triangle and that blue rectangle have the same area? Okay. And do you guys see that the final velocity of the blue car, final velocity of the cop car is going to be exactly twice the velocity of the blue car? It's it. It's a 2-to-1 ratio. So there's the graphical answer. A little bit faster than all this stuff. There's 2 different ways to solve that. Equation way and graphical. 95, road barrier. The driver of a car going so many kilometers per hour suddenly sees the lights of a barrier so many meters ahead. It takes like a fraction of a second to apply the brakes. Yeah, you guys remember doing that reaction time lab? You dropped the ruler and said, how much time does it take to catch it? It's going to be like a delay, right? And then the car accelerates at this value while it's braking. Notice they gave the acceleration as a negative value because the car's braking to stop. Right? Determine whether the car hits the barrier. And then there's a follow-up question, but let's answer that first question first, and then we'll take a look at the other part later. Okay, zoom out for you guys. Okay. All right. What's this? See if you can draw the picture before I draw the picture. So, got road, car. This guy's driving at some initial velocity. I'll go make a number here in a minute. Okay. and then sees this barrier that's just in the road ahead, right? It's some distance. Okay. Yeah, I'll make up a number for that. Okay. Let's say it's like, this numbers are pretty. Let's call this 50 meters. Let's say initial velocity was, 100 kilometers per hour. That's about 60 miles an hour, by the way. Okay. And let's say the delay time before he could hit the brakes was half a second. Okay. And let's have the acceleration of the car after it hits the brakes, right? No, not at first. Okay. Be -9 meters per second squared. Okay. So in that situation, right, so this guy's driving this fast, okay, for this much time at constant speed, and then hits the brakes, then comes to a stop somewhere. Okay. Do you guys think that we could probably solve this and just figure out where he would stop? And if it's before 50 meters, he's okay. And if it's after 50 meters, he's in trouble. Right? And it's really going to be two parts that we're going to put together, because there was a brief time interval that was actually driving at constant speed. Okay? So let's do that first. Let's say that the constant speed part, so I'll call it x of 1. Isn't that just speed times time? Sorry, one more thing. Your book did this. They gave you kilometers per hour, but everything else is in meters and seconds. We have to do a conversion first before I do any of that stuff. Okay. Let's take 100 kilometers per hour and convert that to meters per second. See if you can beat me to the answer. 100 kilometers per hour to meters per second. What's the equivalent value? Well, I know that there are 1,000 meters in 1 kilometer. I also know that 1 hour is equivalent to 3,600 seconds. Now, kilometers goes goodbye. Hours goes goodbye. And look at the unit left on the board. Meters per second. You guys remember doing all this dimensional analysis? Yeah, there you go. All right, so let's see what the speed would be in meters per second, because otherwise I can't apply the equations. I need matching units. Okay. That's looking like 27.78 meters per second. Okay. All right. Guys good? Okay, and that looks about right, so I can believe that number. All right. Now we can apply these equations. I want to figure out how far did the car go. All right. Let's say even absent the barrier, how far would it have gone? So the first distance it goes is just speed times time. And that was 27.78 meters per second. For that delay time before the driver could hit the brake, so that's half a second. And let's see what that comes out to. Was 27.78 times 0.5. That is 13.89 meters. Okay. Now that, let's look at the context of that. Remember, the driver started 50 meters behind the barrier. What's in here? Okay. So looks like he's already used almost 14 of those meters just switching his foot over to the brake pedal. Okay, guess that. Okay. Now how about the rest of this? Well, he's gonna brake. So just to cut to the part that we care about, I'm gonna pick this equation. Okay, and the reason I'm picking this one is, well, I know everything except for the stopping distance, if I think about it. Okay. Because I'm going to assume that the barrier isn't there for a moment, just see like how far would he naturally come to a stop. And stop would mean that there's 0 meters per second. I know his original speed was the 27.78 meters per second. Now don't forget that's being squared. Squared. Okay. And he's also slowed down at a rate of 9 meters per second squared, according to my numbers. Could we just go solve for x? Let's see, it's just going to be some algebra steps, right? So I'm going to take the 27.78, square that, subtract that over. get -771 is equal to -18. X divided both sides by -18. I'm getting the stopping distance as 42.87 meters. Is that? Okay. No, that's just the slowing down part. Okay. So this first part was at constant speed, and the second part was slowing down. Right, so while it was braking, right? And guys, if you put those two together, go back to the original picture, with my numbers anyway. Okay. Would my driver have slammed into the wall? What do you guys think? Yes, because these two numbers add up to more than 50 meters. It would have taken him more than 50 meters from to stop, whatever 13 plus 42 is, right? And so he's going to run down the road. He's going to hit this barrier, right? Okay. Now the follow-up question was, what if he just barely came to a stop? How fast could he go at maximum so that he just barely comes to stop? Like he's just barely tapping that barrier. Right? And what I'll say about that is that what you would do is let these distances go exactly the given distance, like 50 meters in my case. And then you'd have to go back and solve for V0, which is incorporated in both of these. So you could do that. That would be the setup. I think you guys can figure that out, right? You guys have a good Tuesday. Oh, we'll do a lab tomorrow, so I will see you then for that.